Early February, 1943. Guadalcanal, Solomon Islands. A young marine pilot settled into the cockpit of an F-4U Corsair as dawn broke over Henderson Field. The massive Pratt Whitney R-2800 radial engine sat in front of him like a wall of cylinders and steel, 1,800 cubic inches of displacement producing 2,000 horsepower. He advanced the throttle, and the engine roared to life with a sound that seemed to shake the coral beneath the runway. The massive 13-foot propeller bit into the tropical air, and as the Corsair lifted off from the makeshift airstrip, accelerating past 300 miles per hour, the pilot knew he was flying something fundamentally different from anything the enemy had encountered before. What Japanese pilots across the Solomon Islands did not yet understand was that American aviation engineers had achieved something Imperial Japan's aircraft industry could never match: a combination of raw power, structural strength, and manufacturing precision that would transform aerial combat in the Pacific. The Corsair's bent-wing silhouette would soon become synonymous with American air superiority, but the true revolution lay not in its distinctive shape, but in the engine that powered it. A radial power plant so advanced, so meticulously engineered, that it represented an entire generation's leap forward in aviation technology. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how this advantage came to exist begins not with the war, but with a 1938 specification from the United States Navy's Bureau of Aeronautics. The Navy demanded something audacious: a carrier-based fighter capable of exceeding 400 miles per hour in level flight. At that time, most fighter aircraft struggled to reach 350 miles per hour. The specification seemed almost impossible. But Chance Vaught's chief designer, Rex Beisel, understood that meeting such a requirement would require thinking beyond conventional design parameters. It would require building an aircraft around the most powerful engine available, accepting whatever design complications that choice imposed. The engine Beisel selected was still in development: the Pratt Whitney R-2800 double wasp. This was not a refinement of existing technology. This was an entirely new class of aviation power plant. 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches, designed from the outset to produce power levels that contemporary engines could barely approach. When the first prototype XF4U-1 took to the air on May 29, 1940, piloted by Lyman Bullard Jr., it was powered by an R-2800 that generated 1,850 horsepower for takeoff and 1,460 horsepower at 21,500 feet. On October 1, 1940, during a test flight between Stratford, Connecticut and Hartford, the prototype achieved a ground speed of 405 miles per hour with tailwind assistance. The aviation press took notice. This was the first American single-engine fighter to reach such speeds. But what impressed engineers more than the raw velocity was what the achievement represented: an airframe and engine combination that could sustain such performance reliably, repeatedly, without catastrophic mechanical failure. The engineering challenge of harnessing this power was immediate and substantial. An engine producing nearly 2,000 horsepower required a propeller large enough to absorb that power efficiently. Beisel's team designed a Hamilton Standard hydromatic 3-blade propeller measuring 13 feet 4 inches in diameter, the largest ever fitted to a fighter aircraft at that time. This created an immediate problem: how to provide ground clearance for such an enormous propeller while maintaining the structural efficiency required for carrier operations. The solution became Corsair's most recognizable feature. Rather than using conventional straight wings with impossibly long landing gear, Beisel's engineers created an inverted gull wing design. The wings angled downward from the fuselage before leveling out, creating a distinctive profile when viewed from any angle. This configuration allowed relatively short, sturdy landing gear while providing the necessary propeller clearance. The anhedral angle, where the wing met the fuselage, also created optimal aerodynamic conditions, minimizing drag without requiring complex wing root fairings. But the bent wing was merely the visible manifestation of deeper engineering excellence. The real story lay in what American industry could produce: the R-2800 engine itself. This power plant represented decades of accumulated knowledge in metallurgy, precision manufacturing, and thermodynamic engineering. Its 18 cylinders were machined to tolerances measured in thousandths of an inch. The two-row radial configuration required exceptional precision in component manufacture and assembly. Each cylinder had to be precisely identical to every other cylinder. Each piston had to fit its cylinder with exact clearances. The crankshaft had to be perfectly balanced to handle the explosive forces of 18 cylinders firing in carefully timed sequence. The two-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. This was not technology that could be easily replicated. It required sophisticated machine tools, skilled workers who understood precision tolerances, and quality control systems that could ensure consistency across thousands of engines. It required an industrial base that had been developing these capabilities for decades, investing in research, tooling, and workforce training on a scale that few nations could match. By the time production F4U-1 Corsairs began reaching operational units in late 1942, the R-2800 had evolved into the R-2800-8B series double wasp, producing 2,000 horsepower for takeoff. This represented power output that Japanese radial engines simply could not match. The Nakajima Sakae 14-cylinder radial that powered the famous Mitsubishi A6M0 fighter produced approximately 1,100 horsepower. The difference was not incremental, it was fundamental. The United States Navy received its first production F4U-1 on July 31, 1942. But getting the Corsair into actual combat service proved difficult. The long nose and the pilot's position far aft in the fuselage created severe visibility problems during carrier landing approaches. The powerful engine generated enormous torque that made the aircraft challenging for inexperienced pilots, particularly during the critical moments of a carrier landing. The tendency to bounce on touchdown, combined with poor forward visibility and sensitive control responses, led to numerous landing accidents during carrier qualification trials. The Navy made a pragmatic decision. Rather than delay introduction while solving the carrier landing problems, they would give the Corsair to the Marine Corps for land-based operations and adopt the more docile Grumman F-6F Hellcat as the primary carrier fighter. This decision proved fortuitous. The Marine Corps desperately needed a modern fighter to replace their obsolete Grumman F-4F Wildcats, particularly for operations in the Solomon Islands, where Japanese bombers attacked at altitudes the Wildcats struggled to reach. Marine Fighter Squadron VMF-124 received the first combat-ready Corsairs, deploying to Henderson Field on Guadalcanal on February 12, 1943. The squadron's arrival marked a turning point in the aerial campaign over the Solomon Islands. For more than a year, Marine and Navy pilots had faced Japanese fighters on roughly even terms, using tactics and determination to compensate for aircraft that were often inferior to the enemy's. The Corsair changed that equation decisively. The aircraft's first combat encounter occurred on February 14, 1943, in what became known as the St. Valentine's Day Massacre. The engagement was disastrous. 9 American aircraft were lost, including 2 Corsairs and multiple P-38, Lightnings, P-40 Warhawks, and bombers. Japanese defenders lost only a single Zero fighter. The 9-to-1 loss ratio in Japan's favor was so severe that daylight bombing missions to Bougainville were temporarily suspended. This engagement demonstrated a crucial reality. Superior technology alone could not guarantee victory. Tactics, experience, and proper deployment mattered equally, but American pilots adapted with remarkable speed. They learned that the Corsair's strengths lay not in turning dogfights where the nimble Zero excelled, but in what became known as boom and zoom tactics. The Corsair could not outturn a Zero in slow-speed maneuvering, but it could outdive, outclimb, and outrun any Japanese fighter in service. Proper tactics meant maintaining speed and altitude advantage, diving on enemy aircraft, firing, and using superior speed to disengage before the enemy could respond. Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace on May 13, 1943, mastering these tactics and eventually achieving 21 victories. His success demonstrated what the Corsair could accomplish in skilled hands, not aerial ballet, but devastating hit-and-run attacks that exploited the fundamental performance advantages American engineering had built into the airframe and engine. As the war progressed through 1943 and into 1944, the Corsair's reputation grew exponentially. Marine squadrons flying from hastily constructed coral airstrips across the Solomon Islands exploited the aircraft's ruggedness to devastating effect. The Corsair proved capable of absorbing battle damage that would have destroyed lighter Japanese fighters. Its 650 caliber Browning machine guns, with the 4 inboard guns carrying 400 rounds each and the 2 outboard guns carrying 375 rounds each, totaling 2,350 rounds, provided overwhelming firepower compared to the Zero's 2 20mm cannons and 2 rifle-caliber machine guns. The contrast in design philosophy was stark and revealing. Japanese designers had created the Zero by ruthlessly minimizing weight. They eliminated armor protection for the pilot. They refused to install self-sealing fuel tanks, which would have added weight and reduced fuel capacity. They designed every component to be as light as structurally possible, accepting vulnerabilities in exchange for exceptional maneuverability and range. The result was an aircraft that could outturn almost any opponent, but often burst into flames or disintegrated when hit by heavy machine gun fire. American designers took the opposite approach. The Corsair incorporated 150 pounds of armor plate, protecting the cockpit, and a 1.5-inch thick bulletproof glass panel behind the windscreen. The fuel tanks used self-sealing technology, multiple layers of rubber compounds that swelled when punctured, preventing catastrophic fuel loss. These protective features added weight, but the massive power of the R-2800 engine compensated. The Corsair could carry protective armor without sacrificing performance because American industry could produce an engine powerful enough to overcome the weight penalty. This fundamental difference in capability reflected deeper industrial disparities. American refineries produced aviation gasoline of exceptionally high quality and in enormous quantities. American factories manufactured precision components with consistent quality. American workers had access to the best tools, the best training, and worked in facilities safe from enemy bombing. Japan possessed none of these advantages, and as the war progressed, the gap widened relentlessly. By mid-1944, Chance Vought was producing 300 Corsairs per month, 1 complete aircraft every 82 minutes. Additional production came from Goodyear, which built FG Series Corsairs, and Brewster, which produced F-3 A-Series aircraft until quality problems forced cancellation of that contract. Total production across all manufacturers would eventually exceed 12,500 Corsairs, the longest production run of any piston engine fighter in American service. The Corsair's versatility extended beyond air-to-air combat. By mid-1944, Corsairs regularly carried external ordnance, 1,000-pound bombs on centerline and wing racks, 8 5-inch high-velocity aircraft rockets, or napalm canisters. This fighter-bomber capability made the Corsair invaluable for close air support during amphibious operations. During the Okinawa campaign in 1945, Corsairs flew thousands of ground attack sorties, earning the nickname Angels of Okinawa from grateful infantrymen who watched the bent-wing fighters devastate enemy positions. What Japanese pilots encountered in combat told only part of the Corsair's story. From the cockpit of a Zero fighter, a Japanese pilot saw an opponent that defied expectations. The Corsair was larger, heavier, more powerful. When it dove from altitude, it accelerated to speeds the Zero could never match. When it climbed, the massive radial engine pulled it upward at rates that seemed impossible for such a large aircraft. And when it fired, the concentrated firepower of 650 caliber machine guns could shred a Zero's unarmored structure in seconds. Japanese naval aviators were among the most experienced and skilled fighter pilots in the world when the Pacific War began. They had trained rigorously, often for years before seeing combat. They had fought in China, developing tactics against Soviet-supplied fighters. They understood aerial combat at the highest level, But experience and skill could not overcome fundamental disparities in aircraft performance, and as 1943 progressed into 1944, those disparities became impossible to ignore. At a conference convened at Rabaul on April 17, 1943, to discuss lessons from recent combat operations, Japanese commanders expressed growing concern about new American aircraft. While Corsair numbers remained relatively small, their performance characteristics worried Japanese planners. The Americans had fielded a fighter that combined speed, firepower, structural strength, and operational range in ways that challenged every assumption about carrier-based fighter design. Japanese Navy General Staff at Rabaul acknowledged that the Corsair, with its exceptional horizontal speed, was a legitimate match for their fighters. Some officers still considered the Zero superior overall, particularly in maneuverability, but they could no longer claim the complete performance dominance they had enjoyed in the war's opening months. The strategic implications were profound. If American industry could produce fighters like the Corsair in substantial numbers, Japan's aerial superiority would evaporate. The heart of the Corsair's advantage remained the R-2800 engine. Understanding this power plant's capabilities requires examining what American engineering had achieved. The engine's 18 cylinders arranged in 2 rows created inherent complexity. Each cylinder required its own precisely machined barrel, its own piston with rings machined to exact tolerances, its own intake and exhaust valves, its own spark plug. Multiply these requirements by 18, then add the need for perfect synchronization, perfect balance, perfect cooling, and the manufacturing challenge becomes clear. American engine manufacturers had mastered these challenges through decades of development. The tolerances were extraordinary. Cylinder bores were machined to within a few thousandths of an inch of specification. Piston rings had to seal perfectly, while allowing the piston to move freely through millions of cycles. The crankshaft, a massive forging connecting all 18 pistons, had to be balanced so precisely that at operating speeds exceeding 2,000 revolutions per minute, it generated minimal vibration. The 2-stage supercharger system incorporated even more sophisticated engineering. Superchargers compress incoming air before it enters the cylinders, allowing engines to maintain power at high altitudes where air density is lower. A 2-stage system uses 2 compressor stages in sequence, achieving compression ratios that single-stage designs cannot match. This requires precisely manufactured impeller blades, carefully designed internal passages, and intercooling systems to manage the heat generated by compression. Japanese engine manufacturers understood supercharger theory. They attempted to develop comparable systems, but understanding theory and achieving practical results at industrial scale are fundamentally different challenges. Japan lacked the machine tools necessary to produce supercharger components with adequate precision. They lacked the metallurgical expertise to create alloys that could withstand the thermal and mechanical stresses. They lacked the quality control systems to ensure consistency across thousands of engines. The result was that Japanese radial engines, even newer models introduced later in the war, consistently underperformed compared to American designs. The Nakajima Homare 18-cylinder radial, intended to power advanced fighters like the Nakajima Ki-84 Hayate and Kawasaki Ki-100, was designed to produce 1,800 horsepower. In practice, it rarely achieved even 1,600 horsepower reliably, and suffered from chronic overheating and mechanical failures. Meanwhile, American engine development continued advancing. In 1944, Chance Vought introduced the F4U1D variant, powered by the R-2800-8W engine equipped with water injection. This modification allowed the engine to produce up to 2,250 horsepower for short periods at war emergency power settings. Water methanol injection cooled the air-fuel mixture entering the cylinders, allowing higher manifold pressures without detonation. The power increase was substantial, and it translated directly into improved performance. The F4U1D's maximum speed increased from 417 to 425 miles per hour. Climb rate improved by several hundred feet per minute. Most importantly, these improvements came with no modifications to the airframe itself. The same Corsair flown one day on standard power settings and the next day with water injection became measurably faster and more capable simply because of what the engine could produce. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But the true revolution came with the F4U4 variant, introduced in early 1945. This model represented a comprehensive upgrade centered on an even more powerful version of the R-2800, the -18W engine. This power plant produced 2100 horsepower for takeoff under normal conditions. With water methanol injection activated, it could achieve 2450 horsepower for approximately 5 minutes of war emergency power. To handle this enormous power increase, engineers made several modifications. The 4-bladed propeller replaced the earlier 3-blade design, providing more efficient power absorption and better thrust characteristics. The engine cowling was redesigned with a distinctive chin scoop to feed air to the turbo supercharger and intercooler. Internal fuel tanks in the wings were eliminated in favor of external drop tanks, reducing vulnerability to battle damage while improving roll rate. The performance gains were staggering. The F4U4 achieved a maximum speed of 446 miles per hour at 26,200 feet. Some sources reported speeds exceeding 450 miles per hour under optimal conditions. The rate of climb reached nearly 4,000 feet per minute at sea level. This made the F4U4 one of the fastest piston engine fighters in the world, faster than the latest variants of the German Focke-Wulf FW190, faster than late-model Spitfires at low altitude, and vastly faster than any Japanese fighter in service. From the perspective of a Japanese pilot encountering an F4U4 inches combat, the experience must have been profoundly demoralizing. Here was an American fighter that could choose when and how to engage. If the Corsair pilot wanted to fight, he could dive from altitude with overwhelming speed, fire, and climb away before the Japanese pilot could react. If he wanted to disengage, he could simply apply full power and accelerate away, knowing that no Japanese fighter could catch him. The tactical options available to Japanese pilots narrowed dramatically. They could attempt mass attacks, hoping that sheer numbers would overwhelm the escorts despite individual performance disadvantages. They could refuse combat entirely, preserving their aircraft and pilots for more favorable opportunities. Or they could engage and likely be shot down by Corsairs that were faster, more powerful, better protected, and flown by American pilots, who grew increasingly confident and aggressive as their material advantages became undeniable. The psychological effect on Japanese pilots was significant and measurable. Already outnumbered and facing superior Allied production capacity, they now confronted American fighters that seemed to have unlimited performance margins. Experienced Japanese pilots who had survived the war's early campaigns understood what they faced. They had seen the gradual erosion of Japan's qualitative advantages. They had watched as American aircraft evolved from inferior to competitive to superior, and they understood that the trend would only continue. The manufacturing story behind these engines deserves examination. Pratt and Whitney's production facilities in East Hartford, Connecticut, operated around the clock throughout the war. The factory employed tens of thousands of workers, many of them women who had taken manufacturing jobs to support the war effort. They worked with precision machine tools, measuring instruments, and quality control procedures that ensured every engine met exacting specifications. The scale of production was extraordinary. Between 1941 and 1945, Pratt & Whitney produced over 165,000 R-2800 engines in various configurations. These engines powered not just Corsairs, but also P-47 Thunderbolts, A-26 Invaders, B-26 Marauders, and numerous other aircraft. The production rate at peak output exceeded 500 engines per day across all variants. Each engine required approximately 5,000 individual parts, from massive cylinder forgings to tiny valve springs. Every component had to be manufactured to specification, inspected, and assembled correctly. The logistics of coordinating this production were staggering. Raw materials had to arrive on schedule. Specialized components from subcontractors had to integrate seamlessly. Finished engines had to be tested, shipped, and installed in aircraft. Japan possessed nothing comparable to this industrial infrastructure. Japanese aircraft engine. Production peaked at approximately 55,000 engines of all types during the entire war. Quality was inconsistent. Many engines failed to achieve their rated power output. Maintenance intervals were shorter than American engines. Reliability was poor compared to American standards. The contrast extended beyond just engines. American aviation fuel was superior. American lubricants were better. American maintenance procedures were more systematic. American supply chains ensured that replacement parts arrived when needed. American training gave pilots hundreds of hours of flight time before they entered combat. Every aspect of the American aviation system functioned at a level Japan could not match. By late 1944, the strategic situation for Japan had become desperate. The Battle of the Philippine Sea in June 1944, known to American participants as the Great Marianas Turkey Shoot, demonstrated the overwhelming superiority American forces had achieved. Allied fighters and anti-aircraft guns shot down over 500 Japanese aircraft, while losing only 123 American planes. The casualty ratio was catastrophic for Japan, and irreplaceable experienced pilots died in large numbers. The Corsair played a significant role in this aerial massacre. Marine and Navy Corsair squadrons flew combat air patrol missions over the American fleet, intercepting Japanese strike packages before they could reach the carriers. The Corsair's high climb rate and excellent high-altitude performance made it ideal for this mission. Japanese bombers and torpedo planes, flying at medium altitudes and loaded with ordnance, were easy targets for Corsairs that could dive from above with enormous speed advantages. During the Okinawa campaign in 1945, the Corsairs' role evolved again. Japanese forces launched massive kamikaze attacks against the American fleet, sending nearly 1,000 suicide aircraft against the invasion force. Corsairs provided the first line of defense, intercepting kamikaze formations before they reached the fleet. The Corsairs' speed advantage over Japanese aircraft became critical. The aircraft could climb rapidly to intercept altitude, engage multiple targets, and still retain enough fuel and ammunition for extended patrols. The Corsairs' structural strength proved equally valuable. Kamikaze aircraft often required multiple hits to destroy, as Japanese pilots would continue flying even after sustaining damage that would have forced a conventional fighter to break off. The Corsairs' 6 50-caliber machine guns, firing armor-piercing incendiary ammunition at a combined rate of over 4,000 rounds per minute, provided the firepower necessary to destroy targets reliably before they could reach American ships. Marine and Navy pilots developed tremendous respect for their aircraft during these campaigns. They nicknamed the Corsair the Sweetheart of Okinawa and Angel of Okinawa for its role in protecting ground forces. Infantrymen fighting on the island watched Corsairs attack Japanese positions with bombs, rockets, and strafing runs, providing close air support that saved countless lives. The Corsair had evolved from a pure fighter into a multi-role aircraft capable of excelling at air superiority, interception, ground attack, and close air support missions. The ultimate expression of Corsair performance came with the F4U-5 variant, first flown on December 21, 1945, after the war had ended. This model featured the R-2800-32E engine with an even more advanced two-stage supercharger, rated at a maximum of 2,760 horsepower. The cowling was lowered 2 degrees to improve forward visibility. The aircraft featured all-metal wings, eliminating the fabric covering used on earlier variants. Automatic controls managed the supercharger, cowl flaps, and intercooler doors. The F4U-5's maximum speed reached 470 miles per hour, or 408 knots. The climb rate at sea level exceeded 4,850 feet per minute. This was performance that approached early jet fighters, achieved by a piston-engine aircraft through sheer engineering excellence and overwhelming power. The F4U-5 never saw combat in World War II, but it would prove its worth in Korea, where it served with distinction in both fighter and ground attack roles. The story of the Corsair's engine development represents American industrial warfare at its most effective. Victory belonged not just to the side with more aircraft, but to the side that could produce aircraft with fundamentally superior performance characteristics. The R-2800 engine, in its various configurations, provided the Corsair with power levels that Japanese engines could never match. This power translated into speed, climb rate, payload capacity, and operational flexibility that defined American air superiority in the Pacific. Japanese engineers and intelligence officers understood what they faced. They examined captured American aircraft when opportunities arose. They analyzed combat reports from their pilots. They attempted to develop responses, but understanding the problem and solving it were entirely different challenges. Japan lacked the industrial infrastructure, the material resources, the trained workforce, and the manufacturing precision necessary to produce engines comparable to the R-2800. As 1945 progressed, and American forces closed on the Japanese home islands, the disparity became absolute. By the spring of 1945, as Allied armies advanced on Japan from every direction, the Luftwaffe had effectively ceased to exist as a coherent fighting force. American B-29 superfortresses flew over Japanese cities with increasing impunity, systematically destroying what remained of Japan's industrial capacity. The Imperial Japanese Navy had been shattered at Leyte Gulf, Iwo Jima had fallen, Okinawa was under assault, and in the skies over these battlefields, Corsairs dominated with a thoroughness that left no doubt about the war's inevitable conclusion. The final accounting of the Corsairs' combat record tells a story of technological superiority translated into battlefield dominance. The aircraft achieved an official kill ratio of 11-1 against Japanese aircraft. American pilots flying Corsairs shot down 2,140 Japanese aircraft while losing only 189 Corsairs to enemy action during World War II. These numbers reflected not just the Corsairs' technological advantages, but the entire American war machine's superiority. Better training, superior logistics, overwhelming production capacity, and advanced technology at every level. But statistics alone cannot convey what these numbers meant in human terms. Each destroyed Japanese aircraft represented a pilot killed or wounded, experience lost, industrial capacity wasted building replacements that were themselves quickly destroyed. Japan entered the war with approximately 3,500 trained naval aviators. By mid-1944, the majority of these experienced pilots were dead. Their replacements received minimal training due to fuel shortages and the loss of training aircraft to American attacks on Japanese airfields. By late 1944, Japanese pilots reached operational units with perhaps 100 hours of total flying time, compared to American pilots who typically had 300 to 500 hours of training before entering combat. This experience gap, combined with aircraft performance disparities, created impossible odds. Even skilled Japanese pilots in the best aircraft available stood little chance against well-trained American pilots flying Corsairs with overwhelming performance advantages. The contrast between American and Japanese operational situations in late 1944 and early 1945 was stark and unforgiving. Allied fighters could fly multiple combat missions daily, limited only by pilot fatigue and routine aircraft maintenance. Corsair squadrons operated from well-supplied bases with adequate fuel, ammunition, spare parts, and trained maintenance personnel. When an aircraft required an engine change, a fresh R-2800 arrived from the supply chain, was installed by experienced mechanics, and the aircraft returned to combat within hours or days. Japanese fighters often sat grounded for lack of fuel. When they did fly, they operated under strict fuel conservation measures that limited combat capability. A Japanese pilot who burned too much fuel maneuvering in combat might not have enough remaining to return to base. This operational constraint had strategic implications that extended far beyond individual engagements. Japanese fighters could not maintain standing patrols, could not react aggressively to threats, could not sustain operations continuously. They had to pick their moments carefully, conserve fuel rigidly, and often break off combat not because they were losing tactically, but because they were running low on fuel operationally. Allied pilots flew knowing their aircraft were fast, their fuel was plentiful, their support system was robust. This confidence translated into aggressive tactics, better combat results, and higher survival rates. When a Corsair pilot encountered Japanese fighters, he knew he could engage or disengage at will based on tactical advantage. If the situation favored combat, he could attack with confidence. If the odds were unfavorable, he could simply apply full throttle and accelerate away, knowing no Japanese fighter could catch a Corsair at full power. The manufacturing story behind the Corsair's dominance deserves final examination. By the war's end, 3 manufacturers had produced over 12,500 Corsairs in 13 production versions during the period from 1942 to 1952. Chance Vought built the majority, but Goodyear contributed substantial numbers of FG series aircraft, and Brewster managed to produce several hundred F3A series Corsairs before quality problems forced cancellation of their contract. This production scale represented industrial mobilization that Japan could never match. Each Corsair required approximately 15,000 individual parts, from major structural components to tiny fasteners. The inverted gull wing design required sophisticated tooling and precise manufacturing to maintain the compound curves and critical angles. The R-2800 engine alone contained approximately 5,000 parts, each manufactured to exacting specifications. American factories produced these aircraft and engines with remarkable consistency. Quality control procedures ensured that parts were interchangeable across manufacturers. A Goodyear-built FG-1 could use a Pratt Whitney engine from any production batch. Replacement parts from any supplier would fit correctly. This standardization reflected manufacturing sophistication that Japan's dispersed, often primitive production facilities could not achieve. The broader context of American industrial capacity in 1944 and 1945 operated at levels that seemed almost miraculous to observers who understood the scale involved. Factories produced bombers by the thousands, fighters by the tens of thousands. Shipyards launched Liberty ships faster than Germany could sink them. Oil refineries produced aviation gasoline in quantities that exceeded Germany's total fuel production across all grades. Steel mills produced more steel in a month than Japan produced in a year. This industrial dominance resulted from decades of development, vast natural resources, a protected homeland safe from enemy bombing, and a mobilized workforce that included millions of women who took factory jobs to support the war effort. The United States possessed advantages in every category that mattered for industrial warfare: resources, infrastructure, skilled labor, capital investment, technological knowledge, and organizational capability. The Corsair embodied all these advantages in a single airframe. The massive R-2800 engine represented American metallurgy, precision manufacturing, and engineering expertise. The inverted gull wing demonstrated sophisticated aerodynamic knowledge and manufacturing capability. The armor protection and self-sealing fuel tanks reflected a design philosophy that valued pilot survival. The 650 caliber machine guns represented ordnance production systems that manufactured weapons by the millions with extraordinary consistency. Japanese engineers examining captured Corsairs understood all of this. They could measure performance gaps, analyze manufacturing differences, calculate resource disparities. Their reports documenting these findings served as acknowledgments of Japan's failed attempt to match American industrial might. But understanding the problem and solving it were fundamentally different challenges, and by 1945, Japan had neither the time nor the resources to close gaps that represented decades of industrial development. The final months of the Pacific War saw Corsairs operating with complete freedom. By March 1945, missions over Japan often encountered no aerial opposition. Japanese fighters that did attempt to engage were quickly destroyed. The few remaining experienced Japanese pilots understood they were flying obsolete aircraft against overwhelming odds, but they flew anyway, driven by duty and the knowledge that their homeland faced invasion. On August 6th and 9th, 1945, atomic bombs destroyed Hiroshima and Nagasaki. On August 15th, Emperor Hirohito announced Japan's surrender in a radio broadcast. The war that had begun with Japanese aerial supremacy ended with American fighters controlling the skies so completely that Japanese aircraft rarely left the ground during the war's final weeks. The Corsairs' story did not end with Japan's surrender. The aircraft's excellent performance and robust construction ensured a long post-war career. When North Korea invaded South Korea on June 25, 1950, launching the Korean War, Corsairs were among the first American aircraft to respond. They flew from carriers offshore, providing close air support for United Nations ground forces and interdicting North Korean supply lines. In Korea, the Corsair proved that a well-designed piston engine fighter could remain effective even as jet aircraft took over air superiority missions. The F-4U-4 and F-4U-5 variants served with distinction in ground attack roles, their heavy armament and ability to carry substantial bomb loads making them valuable for close air support missions. The aircraft's ruggedness allowed it to absorb ground fire damage and return to base, a critical capability for aircraft operating over hostile territory. One of the Korean War's most remarkable aerial victories occurred when Marine Captain Jesse Folmar, flying an F-4U-5 Newton's night fighter variant, shot down a Soviet-built MiG-15 jet fighter in night combat. Folmar became the first and only piston-engine pilot to destroy a MiG-15 in air-to-air combat, a testament both to his skill and to the Corsair's continuing combat effectiveness nearly a decade after its introduction. The last American combat missions flown by Corsairs occurred in 1953 as the Korean War ended, but the aircraft's service continued with foreign air forces for years afterward. France operated Corsairs extensively in colonial conflicts in Indochina and Algeria. The French Navy's Flottille 12F and 14F flew F-4U-7 variants, a special model built specifically for French requirements, with the R-2800-18W engine and provisions for carrying rockets and bombs. The final combat missions by Corsairs occurred during the brief soccer war between Honduras and El Salvador in July 1969. On July 17, 1969, Honduran Captain Fernando Soto, flying an F-4U-5, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs. The final combat victories for the type were ironically achieved against other Corsairs, a fitting if tragic end to nearly 30 years of combat service. From its first flight in 1940 to its final combat missions nearly 3 decades later, the Corsair proved one of aviation history's most successful and long-lived fighter designs. The aircraft participated in every major American military operation from Guadalcanal to Korea, served with distinction in multiple roles, and earned the respect of both the pilots who flew it and the enemies who faced it. For Japan, the encounter with the Corsair was part of a larger reckoning with technological reality. Japanese engineers and scientists who had struggled against material shortages and industrial limitations during the war worked with American occupation authorities after 1945 to rebuild Japanese industry. The lessons learned from examining American technology, including the Corsair, influenced post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in the hard lessons learned when Japanese engineers examined what American industry could produce. They had confronted engineering excellence and manufacturing sophistication that their wartime industry could never match. The acknowledgement of this gap, painful though it was, provided a foundation for rebuilding. The story of the Corsair and its R-2800 engine is ultimately a story about industrial warfare and the decisive advantages that accrue to nations with superior manufacturing capacity. The purple-dyed high-octane fuel that powered P-51 Mustangs over Europe had its Pacific equivalent in the massive radial engines that powered Corsairs over Japanese-held islands. Both represented American technological and industrial superiority, expressed through petroleum chemistry, precision engineering, and manufacturing excellence. Japanese pilots who faced Corsairs in combat understood they were fighting against more than just an aircraft. They faced an entire industrial system that could produce fighters with performance characteristics beyond anything Japan could match, in quantities Japan could never approach, supported by logistics Japan could not duplicate, flown by pilots trained to standards Japan could no longer achieve. The numbers tell part of the story. 2,140 Japanese aircraft destroyed, 189 Corsairs lost to enemy action, an 11-to-1 kill ratio maintained across 2 years of intense combat. over 12,500 Corsairs produced, service extending from 1943 to 1969 across multiple conflicts and numerous air forces. But the deeper story lies in what these numbers represented. American engineers had designed an aircraft around the most powerful engine they could obtain, accepting design complications to harness that power. American manufacturers had produced that engine by the hundreds of thousands, maintaining quality standards across massive production runs. American industry had supplied fuel, ammunition, spare parts, and trained personnel to keep Corsairs flying combat missions continuously. American training had produced pilots capable of exploiting their aircraft's advantages. Japan possessed courage and skill and determination, but these qualities could not overcome the massive technological and industrial advantages their opponent possessed. The Corsair represented what technology properly applied, with adequate resources and sophisticated manufacturing, could achieve. It was evidence of engineering excellence measured not in theoretical performance but in combat victories, not in design studies but in aircraft that flew and fought and dominated the skies over the Pacific. The examination of the F-4U Corsair by Japanese technical personnel during and after the war stands as a watershed moment, the point when Japan's aviation establishment fully grasped the technological chasm that had opened during the war years. It was a lesson written not in propaganda or combat reports, but in aluminum alloys, precision forgings, manufacturing tolerances, and engine specifications that spoke louder than any words about the true nature of American industrial power. When American occupation forces arrived at Japanese aviation facilities in September 1945, they found extensive evidence of Japanese technical intelligence efforts, captured Allied aircraft scattered around facilities, technical reports, drawings, and photographs documenting Japanese attempts to understand Allied technology. The reports were professional, detailed, and ultimately acknowledgements of capabilities Japan could not match. The Corsair they examined has long since vanished, likely scrapped during the chaotic post-war period, but its legacy remains in the lessons it taught about industrial capacity, engineering excellence, and the decisive advantages these provide in modern warfare. Japanese aviation would rise again in the post-war era, building some of the world's most advanced aircraft. But never again would Japanese engineers underestimate what their American counterparts could accomplish when given adequate resources, sophisticated manufacturing capabilities, and the industrial infrastructure to fully realize their designs. The bent-wing fighter that Marine pilots flew from coral airstrips across the Pacific, that Navy pilots launched from carrier decks, that ground troops called the Angel of Okinawa represented more than just an excellent fighter aircraft. It represented the culmination of American aviation engineering in the piston engine era, powered by an engine that embodied decades of accumulated knowledge in metallurgy, thermodynamics, and precision manufacturing. The R-2800 double wasp, in its various configurations producing from 2,000 to nearly 2,800 horsepower, gave the Corsair performance that Japanese fighters could never match. That power difference, measured in horsepower and manifold pressure, in climb rates and maximum speeds, was one of the many differences that decided who would win the war for the Pacific skies. And in that decision lay the fate of Imperial Japan and the demonstration of Allied industrial might expressed through precision engineering, transformed into combat power, and proven in victory one mission at a time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.